Okay, so again, make sure that you understand the meaning of solve. Solving means you are trying to find the value or values to make this statement true. So now the question is, well, there are two ways I would like you to think about this. One way is the very procedural way. You'd be like, oh, you want to find x, and that means you want to get rid of the plus one, you want to get rid of the cosine, done. Now, the other way I would really want you to think about is this. I want you to think about that cosine x plus 1 equal to 0. That means cosine x must equal to -1. Now, you may say, well, Mr. Chan, what's the difference? I mean, if I do the procedure of throwing the plus 1 to the other side, you get the same conclusion, isn't it? Well, conclusion, yes, they will be the same. But the initiation of the thought process will be somewhat different. Oh, no, thank you. All right, so the initiation of the concept is quite different. So if you say, well, cosine x plus 1 is equal to 0, so cosine x must equal to -1, then you can start thinking, what do you know about cosine x? What kind of x value would make it -1? Okay, so think about cosine x being equal to -1. So x must equal to pi. Now, for the most part, we'll restrict our domain from 0 to 2 pi. So we just have to worry about the 4 quadrants. Okay, so that's somewhat easy. Now, how about this? I will let you try number 2. Go ahead, try number 2. So we say, well, sine x is equal to 1/2. And if sine x is equal to 1/2, what must or what could x be? Pi over 6, and it could also be 5 pi over 6. So there are 2 answers. Okay, now you might be asking, you might be thinking a question. You'd be like, wait, hold on. So do we usually have 1 answer or 2 answers? Well, that's a valuable question to ask, but the more important question to ask is, that's why I want to reinforce the idea. We are just trying to find out the x value or x values to make the statement true. If there are only one value to make the statement true, well, the answer will be just 1. But if there are multiple values that could make the statement true, then we include all those values. So while we might want to have a definitive number on the number of solutions, I would just say, well, you know what? It's just whatever it would be, whatever x values could be to make the statement true. Right? Yes. All right, go ahead, try number 3 yourself. I think you can definitely handle number 3 on your own. All right, for number 3, so we have this. We have so we have -1 on the right when we move the +1 over, and then we have tangent x equals to -1 over √3, which you can think about this as -3 over 3. So we ask, so x, what could x be? It's a -3 over 3. So that would be quadrant 2 and quadrant 4. So that would be 5 pi over 6 and 11 pi over 6. Now, and that's kind of the expectation right here. All right, it should take you no more than 3 seconds to get these values, these x values. Yes. Well, if you do the rationalization, you multiply by root 3 over 3, root 3 over root 3, then you have this. Yeah. All right, now, so now go ahead, try number 4 yourself. This one is with secant. Okay, see if you can get it right for secant. So for secant, so now I welcome you to skip some steps. Okay, now you can just go straight to here if you want to. Now let me tell you what I would do. As you know, I am not a fan of those secant, cosecant, or cotangent. So if I see this secant x, which I know it's 1 over cosine, so what I'm going to do is to do the reciprocal. Okay, I'm going to do the reciprocal on both sides. So secant x becomes cosine x, and then the right-hand side will just be the reciprocal. So then I consider my x values and be like, So what x value would give me cosine x equals to negative root 3 over 2. 5 power over 6 and 7 power over 6, quadrant 2 and quadrant 3. Okay, so if you have all those values nailed down, you would enjoy this process very, very much. Okay, so now we get to see some a little bit different kind of taste. Okay, different kind of taste is that for things like number 5, 6, 7, and 8. So we're gonna see something right here. You see some square. All right. So some of you might be thinking about, are we doing those Pythagorean identities, or maybe those double angle identities? Well, the good news is, no, it's not. Simpler. We just jam in with this, jam those trig functions with the quadratic stuff. So now on the one hand, you may use the, you may say, oh, let me use a dummy variable. Let me use a. Okay, I'm going to show you both. So on the one hand, you may say, let me go ahead, use a as sine x. So you have 2a squared minus a minus 1. And you do the factoring like this. You may, but at the same time, I would strongly discourage you from doing that because it's not that hard. I would just say, well, do you think you can just not use a dummy variable and factor? Can you go ahead and factor it this way? Because no one uses dummy variable in calculus. But that's more like an algebra 2 level stuff. Okay, it's new. You may want to get some used to do. But now we're like, no, I think you're good. I think you are capable of just doing it without the dummy variable. So again, we would like to find out the x values, or the x value or x values that make the statement true. So in this case, we have 2 possibilities. One possibility is that this could equal to 0. The other possibility is that this could also become 0. So you just go ahead and explore the possibilities, okay, for these x's. So you say, well, sine x, it's equal to negative 1 over 2. So we say, well, what could the x values be to give us negative 1/2? What that would be 7 power over 6, and also 11 power over 6. And if you feel somewhat confused, and chances are you don't have the unit circle values, And do not find this as a way to get discouraged. Find this as a way to tell yourself that, okay, you got a couple of days to get it done. And I'm still opening the opportunity for anyone who would like to improve your unit circle quiz scores. Okay, so we have two answers based on this possibility. And now let's explore the other one. We say, well, the other one is when you have sine x equals to 1. So what could x be? Yeah, pi over 2. So in this case, we have 3 answers. Okay, we have 3 answers. Now go ahead, try number 6 yourself. Okay, see if you can do this without using a dummy variable. From here to here, just factoring. Like if you do the dummy variable factoring, right? Think about a being sine x. So you just factor the, the algebra 1, algebra 2a. You think about what times what gives you 2a squared, what 2a times a. Which two numbers can, wait, hold on. Remember, I mean, this is a 1, right? Which two numbers can multiply to give you -1? It's got to be +1 and -1. And then you do the FOIL. And how you do the FOIL, you get -a. Well, when you do the outside, you have -2a. Okay, and then you do the inside, you have a. So -2a plus a, you have -a. So what I'm saying is, I'm giving you this as a bridge. I want you to see this. Okay, you can do this with a dummy variable, but I also want you to transition away from the dummy variable. Okay. So for number 6, all right, for number 6, I believe you can factor this. And should be 2 cosine x times cosine x. And both should be minus because you have a plus and a minus over there. So I'm getting this. All right, I'm getting this. 2 cosine x minus 1 times cosine x minus 3. That would be my factors from the trinomial. And then I would have one possibility of 2 cosine x minus 1 equal to 0. And the other possibility is cosine x minus 3 equals to 0. All right, now, can you see something strange? Yeah, cosine minus 3 equals to 0. So you're saying cosine equals to 3? But our understanding is that cosine can go only up to 1. So that's nothing. There's nothing to there's nothing going on from this end of the possibility. You're not going to get anything that would make the statement true. So you put all your hopes on the left-hand side. So you have cosine x equals to 1/2. And then we say, what would x be? Pi over 3. And, no. 5 pi over 3. Yes. 7. When you do that's 7 minus 7 cosine x is the outcome of the outside and inside. So you think about the outside. All right. So you have 2 sine x times minus 3, which is minus 6 cosine x. And then you have minus 1 times cosine x. So minus 6 cosine x minus 1 cosine x gives you minus 7 cosine x. Yeah. All right, now number 7. Now, a lot of people, they got freaked out by number 7, but number 7 is actually quite easy. Okay. So what could you do with number 7? Yeah, just factor the sine x. Okay. don't get scared because there are only two terms. Okay, it's actually pretty straightforward. So that means the two possibilities are sine x equal to 0 or sine x plus 1 equal to 0. So we say x is equal to 0 and pi. And we have sine x equals to -1. So x is equal to 3 pi over 2. Okay. All right, go ahead, try number 8. Go ahead, try number 8 yourself. Try it out. Try it out, number 8. Yes. For number 8, you will factor out the cosine of x. So then you have 2 cosine x minus 1 equal to 0. So your first possibility is cosine x equal to 0. The other possibility is 2 cosine x minus 1 equal to 0. So x is equal to pi over 2 and 3 pi over 2. And then on the other hand, you have cosine equals to 1/2. That means x is equal to pi over 3 and then 5 pi over 3. So we got 4 total answers for this question. Now, after this chapter, this topic, you will become really good with your unit circle values. And this is actually what you would do a lot in calculus. You will see this kind of work constantly in calculus. So that's why last week, at the beginning of the week, I previewed the materials for last week. I was like, all right, the sum and differences. Yeah, something that I have to teach. It's not something that I enjoy a lot, but it's okay. You get to practice your skills with fractions, adding fractions, complex fractions. And now you have something actually quite useful. Okay. Now, what about number 9? Okay. So for number 9, we have a single sine square x right here. So we say sine square x is equal to 3 over 4. And now we will do the square root. So we have square root of 3 over 2. And then we have x equals to pi over 3 and 2 pi over 3. Okay. Any question? Divided 2? There's no 2. Oh, number 8. I'm sorry. Number 8 divided 2 to the other side, like initially. Well, you do it initially, then you have a 2 right here as well, because of subtraction. Yeah. So you don't want to do that. Now, for number 9, if you stop right here, unfortunately, you would not receive full credit. Can anyone see why it would not receive full credit? Louder? Plus or minus? Because this is squared, right? The squared of sine x, it gives you 3 over 4. So not only you consider the positive root 3 over 2, you should also consider that sine x being negative root 3 over 2. So when you take the square root, it has to be a plus or minus square root. So you can also think about what you learned back in algebra 2, the even, odd thing. Okay, even root. even root, even power, and then you have a power of 1 at the end. So that's why you have to have the plus or minus. So one way you can, that's one way you can consider it. The other way to think about it is just that, well, if you have something squared to give you a 3/4, it could mean that the positive or the negative values. So so now we have to come up with the other 2x values, which will be 4 pi over 3 and 5 pi over 3. So whenever you see something that's squared and you have to take the square roots, don't forget that you need to consider the positive and negative. So again, focusing on what makes the statement true will give you a big help. Okay? All right. So now I would like to go to question number, if you go to the back, okay? So stuff will be more or less the same for the rest until question 19. Question 19. Now, question 19 is kind of strange or different because for all the questions in the past, you only have a single x in the parentheses inside the trig function. But for 19, we have 3x. Now, how does this change our process of finding the solution? Well, if you look at the instruction right here, it says solve for x, right? Solve for x, and x will be from between 0 to 2 pi. We got that. So let me go ahead and paste it right here. So we have this little statement right here, solve for x, and x is going to be in between 0 to 2 pi. But this is 3x. So how would this change? Because if we are going to solve for this, well, when we try to solve for this, we will find out what 3x is equal to. But the domain is only for x. So because of this, we will have to change our domain. Well, from x to 3x, that means you have to multiply everything by 3. So instead of from 0 to 2 pi, you would go ahead, okay, and consider the domain from 0 to 6 pi. Okay. So you have what? So think about 1/2. All right, 1/2 would be pi over 6, right? And then 5 pi over 6. But that's just the first revolution. That would be just the answers for 0 to 2 pi. But now we have to consider the second revolution and the third revolution. So we say, all right, so in order to go to the next revolution, we're just going to go ahead and add 12 pi over 6, right, onto these two. Okay, it's going to add 12 pi over 6 onto these two to get our next two values, which will be 13 pi over 6 and then 17 pi over 6. That would be from 0 all the way to 4 pi. But then we have to go all the way to 6 pi. That means we will have to add another 12 pi over 6, which gives us 25 pi over 6, and then 29 pi over 6. Okay, so now let me just recap this. So this one is from 0 all the way to 2 pi. And then all the way to here, this is all the way to 4 pi. And this one is all the way to 6 pi. Okay, that's what 3x is equal to. If you don't account for this change of domain, then we will have a problem. But we want to find x. So we say, well, let's go ahead and multiply both sides by 1/3. So you have pi over 18, 5 pi over 18, 13 pi over 18, 17 pi over 18, 25 pi over 18, and 29 pi over, 29 pi over 18. So you have a total of 6 answers for your solutions. All 6 values here, they will all make the statement true. So again, whenever you see something, when you see a number that's not just x, it's like 2x, 3x, or 4x, then you should sound the alarm, and you'll be like, all right, hold on. We will have to adjust the domain for the moment so that we can account for all the solutions. Okay, you cannot just go from 0 to 2 pi because that's for x. Now, in this particular case, you are dealing with 3x. So now if you go ahead, take a look at number 20. So how should we adjust our domain? We'll say our domain would be from 0 to how much? 8 pi. All right, so I'm going to let you try it. Okay, see if you can get to the solutions. Okay, I'll let you look at this as a little reference. So you have all the way up until 8 pi. Okay, for the 4x, the domain of 4x. Okay, for number 20. So you would have cosine of 4x equals to negative root 2 over 2. So you think about what values would give you root 2 over 2 negative for cosine. So it's going to be quadrant 2 and quadrant 3. So you've got 3 pi over 4 and then 5 pi over 4. Now that's just for the first cycle, first revolution. But you have to go up to 8 pi. So let me squeeze a little bit of space so that I can have more space to add on to this. So to make your list a lot more easier. So basically it will be the same value after 1 revolution. So that means you have to add 2 pi, which is 8 pi over 4. So you add 8 pi over 4 to the first one, becomes 11 pi over 4. And then you add 8 pi over 4 for the next one, you get 13 pi over 4. And basically just repeat the same procedure for a couple more times. So again, that's from 0 to 2 pi. This is up to 4 pi. And then 19 pi over 4. And then 21 pi over 4. That's up to 6 pi. And then you have, what is it called? 27 pi over 4. And then 20, no, hold on, not 27. Wait, yeah, it is 27. And then 29 pi over 4. So that would be up to 8 pi. And then you will divide, or you will multiply by a quarter on both sides. So all the denominators become 16. So so you have, well, just go ahead and change the denominator from 4 to 16. For this one? Yeah, there will be 7 pi over 4 will be quadrant 4. All right. So it's a bit tedious, but we don't see them often. Yes. Like this list. Again, our adjusted domain is from 0 to 8 pi. Okay. So the first 2 values is from 0 to 2 pi. Okay, that's what we usually would do. But because of the adjusted domain, we have to keep going. So for the next 2 values, That will be the second revolution. And that's why I use a little bracket to kind of group them together so you can see better. Okay. Yes. Say again. 8 pi over 4. Now, the idea is add 2 pi because one revolution, right? But then, well, because we have a denominator 4, so that's basically add 8 pi over 4. So from here to here, we add 8 pi over 4. From here to here, we add 8 pi over 4. And we just keep doing the same thing for 4 times for each angle. So then we can get the list of values here. All right. So yeah, so can go ahead and, oh, well, one more thing for question number 21. Now, this one is a little bit different. You may want to highlight this one. Instead of giving you the domain, this time it sets solve for all values. Now, we don't see this often, but you do have to get ready for this. So we say, well, we have tangent square x equals to 3. So we have tangent x equals to root 3, or tangent x equals to negative root 3. Okay. So we have x equals to pi over 3, and also 4 pi over 3, and tangent x is equal to 2 pi over 3, and 5 pi over 3. Right? We have these values, but now these values are only for the first revolution, okay, from 0 to 2 pi. But now we want all values, meaning that doesn't matter how many revolutions you are doing, we want to include all of them. Now, we don't have time to list out all of them, so we want to have an easier way. And since we know it's going to be the same after each revolution, so we can say something like this. X is equal to pi over 3 plus 2k pi every 2 pi. 4 pi over 3 plus 2k pi. Because we're going to have these values after every single revolution. So just go ahead and just say pi over 3 plus 2k pi. And you also have 2 pi over 3 plus 2k pi. And 5 pi over 3 plus 2k pi. Like every 2 pi. Remember how we did the asymptotes before? Okay, we say every pi over 2, every pi, every 2 pi. So this is basically telling people that, hey, we have your solutions. And you're going to see the solutions every 2 pi. Meaning that if you rotate for one circle, you're going to head back to the same value. So that's how you do to include all the values of x, instead of just from 0 to a particular angle value. Okay, so go ahead, try out number 22 yourself. For 22, you factor out the cosine of x. So you have cosine x equals to 0, or cosine of x plus 1 equal to 0. So x is equal to pi over 2. X is equal to 3 pi over 2. X is equal to, well, cosine x is equal to negative 1. So x is equal to pi. And then we just tag on the 2k pi afterwards. Okay, so that's pretty much what you will see for the rest of the week. So let me just do a quick recap, okay, on the stuff covered today. So at the very beginning, we showed you an equation. So now we are actually putting those unit circle values in practical usage. We're like, oh, so we want to solve. Again, solving doesn't mean to find x. Solving, the real meaning of solving is to make the statement true. So then we find out what x values would, or what x value or values could make the statement true. So sometimes you see one answer, sometimes you may see two answers. And the idea is that, well, it's just the whatever x value or values could make the statement true. So for the first four questions, they are pretty much the same thing. If you know the unit circle values, they would be a piece of cake. Now, then you start to see something we mixed with earlier algebraic concepts, such as a quadratic equation. You may need to factor out and then solve for it. And this is very common. You should expect to see this, things like this further down the road. Okay. You have this simple kind of quadratic factoring, or you have something as easy as this one. So don't freak out when you have only two terms. Just factor out whatever that's common. Okay. And then consider the situations, right? The possibilities. All right. And then we also see something like this. When you have to take a square root, make sure that you take the positive and negative square root, plus or minus square roots, because you can have two possible outcomes. Okay. And then the last one, well, the second last one is that you have not x, but you have something other than x. You can have 3x or 4x. If that's the case, make sure that you adjust your domain accordingly. Make sure you adjust your domain accordingly. And then as you find out your values for 3x, make sure you make a list of them. Okay. And then the last one is that instead of telling you to find out values from 0 to 2 pi, we say please find out all the values. All the values. In this case, we will have to use the 2k pi to describe that you will have the solution every single revolution. Okay.